Throughout history, humanity has encountered moments of profound discovery that altered the trajectory of our understanding. These pivotal moments arrive rarely, often emerging from careful observation and rigorous analysis of phenomena that initially seemed beyond comprehension. Tonight's presentation constitutes precisely such a moment. The evidence we will examine has been gathered over decades of systematic research, compiled by thousands of scientists across multiple disciplines and geographic regions. Each piece of data, each measured observation, each replicated experiment contributes to a singular, coherent picture that defies easy dismissal or casual contradiction. What makes this particular finding so significant is not merely its novelty, but rather its explanatory power. It accounts for inconsistencies that have puzzled researchers for generations. It reconciles competing theories that previously seemed mutually exclusive. It provides a framework through which previously isolated discoveries suddenly connect, forming a unified whole that is greater than the sum of its parts. The implications extend far beyond academic circles or specialized fields of study. This understanding touches upon fundamental questions about existence itself, about causation, about the very nature of reality as we perceive and measure it. The shift we are discussing represents a categorical change in perspective. It is not a minor adjustment to existing models or a refinement of accepted theories. Rather, it constitutes a reorientation of how we approach basic assumptions about the world around us. Previous frameworks, while useful in their time and within their limitations, operated from premises that we now recognize as incomplete. This is not to diminish the work of those who came before us. Science progresses through such revisions and expansions of knowledge. Each generation builds upon the foundations laid by earlier thinkers, incorporating new tools, new data, and new analytical capabilities. The journey to this realization has not been straightforward. Resistance emerged from multiple quarters, rooted in legitimate scientific skepticism and attachment to long-standing models. However, as evidence accumulated and methodologies improved, the case became increasingly undeniable. Today, the preponderance of data, examined through multiple independent analytical approaches, points inexorably toward a singular conclusion. This is not a matter of opinion or interpretation, but rather an inevitable consequence of following evidence wherever it leads, regardless of our preconceptions or preferences. When tonight concludes, you will have grasped precisely what this means, and why it fundamentally reshapes how we think about the universe we live in. The term event horizon was coined in the 1950s by a physicist named Wolfgang Rindler, and it describes something that sounds simple but turns out to be one of the strangest concepts in all of physics. The basic definition is this: an event horizon is a boundary in space-time beyond which no event can ever influence an outside observer. Nothing crosses it outward, not matter, not radiation, not a signal of any kind. Whatever happens on the far side stays on the far side, permanently and completely. That might sound like a description of a wall, but here's the critical thing: it isn't one. There's no surface to touch, no barrier to detect as you pass through it. It's a mathematical boundary, a line drawn not by matter or energy, but by the geometry of space-time itself and the finite speed of light. To understand why that matters, think about a river current. Imagine a swimmer in a fast-moving river trying to reach the bank upstream. The The swimmer has a maximum speed. As long as the current is slower than the swimmer, they can make progress. But if the current is faster, there's a point downstream beyond which the swimmer can never return to shore. Not because anything is blocking them, but because the physics simply won't allow it. The current moves faster than any stroke they can manage. That point of no return isn't marked. You can't see it. You could drift across it without knowing, but once you have, upstream is gone forever. Event horizons work the same way. Replace the swimmer with a beam of light, and replace the current with the geometry of space-time, curved by an extreme concentration of mass, or by the expansion of the universe itself. There's a point past which even light, the fastest thing that exists, cannot make it back out. Not eventually. Not with more energy. Never. The physics won't allow it. What makes this genuinely unsettling is the causality part. An event horizon isn't just a barrier to travel, it's a barrier to information. If something happens beyond it, that event can never cause anything on your side of the boundary. The two regions become causally disconnected. What occurs there is, in the most rigorous physical sense, permanently irrelevant to you. You can't know about it. You can never know about it. That's not a limitation of your instruments. That's a feature of how the universe is built. Wolfgang Rindler formalized this concept and gave it the name we use today. Before that, the idea had existed in scattered mathematical forms, buried in the work of physicists who had identified the concept without quite naming it. Rindler clarified something important. Event horizons are observer-dependent. Whether a horizon exists and where it sits depends on who is asking the question and what their motion through space-time looks like. That's a subtle but important point. It means the horizon isn't a fixed object nailed to a particular place. It's a relationship between an observer and the geometry of space-time around them. There are several distinct types of event horizons, and they arise in very different physical situations. The most familiar, the one most people have heard of, is the event horizon surrounding a black hole, where gravity becomes so extreme that escape velocity exceeds the speed of light. A star collapses, space-time curves past a critical threshold, and a region forms from which nothing can escape. The boundary of that region is the event horizon. Everything inside it is cut off from the rest of the universe. But black holes aren't the only place this happens. The expansion of the universe itself can produce event horizons. If space between two regions is stretching faster than light can cross it, those regions lose the ability to communicate. A signal sent from one will never reach the other, not because of gravity, but because space is growing between them faster than the signal can travel. That's a cosmological event horizon, and it wraps around not a single object, but around the entire observable universe. It defines the boundary of what we can ever detect, ever learn, ever know anything about. These two types of horizon, the one around a black hole and the one around the observable universe, are related by the same underlying physics, but they operate at dramatically different scales and arise from completely different mechanisms. One is created by the collapse of mass, the other is created by the expansion of space. One can be in principle avoided if you simply stay far enough away. The other surrounds you right now at a distance of roughly 16 billion light-years in every direction, and you can't do anything about it. We're going to work through both of these, starting with black holes and building outward to the cosmic scale. We'll look at how large these horizons actually are, what it would mean to cross one, and what the existence of a horizon around the observable universe tells us about the limits of knowledge itself. The numbers get staggering fast, and that second kind, the one that wraps around the entire observable universe rather than a single collapsed star, is what this is really all about. In 1916, less than 2 months after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild solved Einstein's field equations from the front lines of World War I and found something nobody had anticipated. Schwarzschild was stationed on the Eastern Front, calculating artillery trajectories by day and working through Einstein's newly published equations at night. The conditions were brutal. He was already ill with a disease he had contracted at the front, and yet, in the middle of a war, surrounded by artillery and mud, he produced a solution to one of the most complex mathematical systems ever written. He mailed the result directly to Einstein. Einstein was reportedly stunned. The equations had only been published weeks earlier, and here was a complete, exact solution arriving from a battlefield. What Schwarzschild had found was a precise description of the geometry of spacetime around a perfectly spherical, non-rotating mass. His solution was elegant, and it worked. But buried inside the mathematics was something deeply strange. There was a specific radius, a critical threshold, at which the equations broke down in a very particular way. At that distance from the center of any massive object, gravity became so extreme that nothing could escape. Not matter, not light, nothing at all. That radius is now called the Schwarzschild radius. The formula looks like this: Rs equals 2gm divided by c squared. G is the gravitational constant, m is the mass of the object, and c is the speed of light. What it tells you is straightforward. The Schwarzschild radius scales directly with mass. Double the mass of an object, and you double the radius of its event horizon. The speed of light appears squared in the denominator, which is why the resulting numbers are so small. Light is extraordinarily fast, and it takes an enormous amount of mass to produce an event horizon of any significant size. Here's where things get concrete. The Sun has a mass of about 2 × 10⁻30 kilograms. Run that through the Schwarzschild formula, and you get a radius of roughly 2.95 kilometers. That's less than 3 kilometers. If you could somehow compress the entire Sun, a star 1.4 million kilometers across, down to a sphere smaller than a mid-sized city, it would collapse into a black hole. Its event horizon would be about the size of a small town. Everything outside that boundary would still feel the same gravitational pull as before. The planets would keep their orbits, but nothing that crossed that 2.95 kilometer threshold would ever come back out. Now apply the same formula to Earth. Our planet has a Schwarzschild radius of about 9 millimeters, the size of a marble. Compress the entire mass of the Earth. Every ocean, every continent, every mountain range, the iron core, all of it, into a sphere 9 millimeters across, and you've created a black hole. That's not a figure of speech. That is what the physics says. This applies to everything. Every object in the universe has a Schwarzschild radius. For most objects, it's buried so deep inside them that it's irrelevant. The object would have to be compressed far beyond any natural process to reach it. A human being's Schwarzschild radius is somewhere around 10 to the negative 25 meters. That's smaller than a proton by many orders of magnitude. You are nowhere near becoming a black hole. but the threshold exists. The formula doesn't care what you're made of. What actually matters is density. A black hole doesn't form just because an object is massive. It forms when that mass is compressed into a small enough volume. The sun is not a black hole because its mass is spread across an enormous sphere. The moment that sphere shrank below 2.95 kilometers, the math changes completely. At that point, the escape velocity at the surface exceeds the speed of light, and the object has no way to prevent continued collapse. Gravity wins, and it wins permanently. This is what makes the Schwarzschild radius so significant. It's not just a number you calculate and file away. It's a threshold. Cross it in the wrong direction, and the laws of physics as you experience them stop applying. Time itself behaves differently near the boundary. An outside observer watching something fall toward a Schwarzschild radius would see it slow down, freeze, and redshift into invisibility, never quite appearing to cross the line. The infalling object, from its own perspective, crosses the boundary in finite time. The two descriptions are both correct and both deeply uncomfortable. Schwarzschild mailed his solution to Einstein in December of 1915, within weeks of the general relativity paper's publication. Einstein presented the result to the Prussian Academy of Sciences in January of 1916, describing it as a clean and remarkable achievement. The concept of a boundary from which nothing escapes wasn't fully appreciated at the time. Most physicists assumed the singularity at the Schwarzschild radius was a mathematical artifact, something that would vanish once the physics was better understood. It took decades for the scientific community to accept that the boundary was real. Schwarzschild never participated in that debate. He died in May of 1916, just months after completing his solution, from the illness he contracted at the front. He was 42 years old. He never knew that the radius bearing his name would eventually be applied to objects spanning millions of kilometers, imaged by telescopes linking continents, and discussed as one of the defining features of the observable universe. Schwarzschild died months after mailing those equations to Einstein, never knowing that the boundary he calculated would become one of the most important numbers in the history of science. Most stellar mass black holes, the kind that form when a massive star collapses at the end of its life, have event horizons that are only a few kilometers across. That number is almost insulting given the violence involved. A star dozens of times more massive than our sun, burning for millions of years, exhausting its fuel, detonating in a supernova, and what's left behind is a boundary you could drive past on a highway in under a minute. That's the Schwarzschild radius formula, doing exactly what it promises. Small mass, small horizon. The relationship is direct and merciless. But here's where things start to get uncomfortable. Not all black holes are stellar remnants. At the centers of most large galaxies, including our own, sit objects of an entirely different category: supermassive black holes. And the word supermassive is doing real work there. These aren't just bigger versions of the same thing. They're a different order of magnitude entirely, and their event horizons reflect that. Take Sagittarius A, say, the black hole sitting at the center of the Milky Way. Its mass is roughly 4 million times the mass of our Sun. Run that through the Schwarzschild formula, and you get an event horizon spanning about 12 million kilometers. Think about what that means for a second. The Sun is about 1.4 million kilometers across. The event horizon of Sagittarius A is roughly 17 times wider than the entire Sun. It's a boundary larger than the distance from the Sun to Mercury. If you placed Sagittarius A stas where our Sun is, Mercury's entire orbit would sit inside it. The innermost planet in our solar system wouldn't orbit that black hole. It would be swallowed by the event horizon before it got anywhere close. And Sagittarius A stas is not even particularly large as supermassive black holes go. It's our local example. It's the one we can observe in the most detail. But the universe contains black holes that make Sagittarius A stas look modest. In 2019, astronomers released the first direct image of a black hole's shadow. That black hole was M87, sitting at the center of Messier 87, a giant elliptical galaxy about 53 million light-years away. M87 has a mass of approximately 6.5 billion solar masses. Not 4 million, 6.5 billion. Its event horizon is so large that it extends beyond the orbit of Neptune. Our entire solar system, from the Sun out to the edge of the known planets, would fit inside the boundary of no return around M87 time. Every planet, every moon, every comet in the outer reaches of our system, all of it would fall within that horizon. You wouldn't be orbiting that black hole from Neptune. You'd already be inside it. That image, by the way, took a planet-spanning telescope network, years of data processing, and petabytes of raw observations just to produce a blurry orange ring. The scale of what was being photographed made it almost impossible to resolve. We'll get into exactly how that worked in the next section, but hold on to the scale for now, because we're not done. TON 618 is one of the most massive black holes currently known. It sits roughly 10.4 billion light-years away, and its mass is estimated at around 66 billion solar masses. 66 billion. At that mass, its event horizon stretches to roughly 1,300 astronomical units across. 1 astronomical unit is the distance from the Earth to the Sun. So the event horizon of TON 618 spans about 1,300 times that distance in radius. The nearest star system to our Sun, Alpha Centauri, is about 276,000 astronomical units away. TON 618's event horizon is a significant fraction of the way there. Not the full distance, but close enough that the comparison stops being abstract and starts being genuinely hard to process. What all of this illustrates is that the Schwarzschild formula isn't just an equation, it's a scaling law. Double the mass, double the horizon. Increase the mass by a factor of 1 billion, the horizon grows by a factor of 1 billion. The physics doesn't care how large the number gets. It just keeps scaling. A stellar mass black hole has an event horizon the size of a city. A supermassive black hole has one the size of a solar system. And given a large enough mass, there's no obvious upper limit written into the formula. That last point matters more than it might seem, because what we've been describing are horizons around individual objects, defined by the mass they contain. But the Schwarzschild radius scales with mass, and mass is everywhere. The observable universe contains an enormous amount of it, spread across billions of light-years, distributed through galaxies and gas clouds and dark matter halos. And if you were to ask what kind of horizon that total mass might imply on a cosmic scale, you'd be asking exactly the right question. The universe has its own version of this boundary. It doesn't work identically to the black hole case, but the underlying logic, mass, gravity, the speed of light, a point of no return, carries through in ways that should, by now, feel familiar. But as enormous as these are, they're nothing compared to the kind of horizon we're building toward. For most of the 20th century, a black hole's event horizon was a purely theoretical concept, a boundary deduced from equations that many physicists weren't sure would ever be possible to directly observe. And that uncertainty made sense. The event horizon of a black hole doesn't glow. It doesn't emit any signal. By definition, nothing crosses it outward. What you'd actually be trying to image is an absence, a region of space from which no light escapes, surrounded by superheated gas that does. That's not nothing, but it's close. And the objects you'd be targeting are either stellar remnants only a few kilometers across, scattered across the galaxy, or supermassive black holes, so distant that even the largest ones subtend an angle on the sky, roughly equivalent to trying to photograph an orange sitting on the surface of the moon, from Earth, with your eyes. So the question wasn't just whether we could do it. The question was whether any instrument we could physically build would be sensitive enough to resolve something that small at that distance. Here's where things get interesting. A single radio telescope isn't powerful enough, not even close. But there's a technique in radio astronomy called very long baseline interferometry. The idea behind it is both elegant and almost unreasonably ambitious. If you link multiple radio telescopes together and synchronize them precisely enough, they don't just add their signals. They effectively function as a single telescope with a diameter equal to the distance between the most widely separated dishes. Combine two telescopes on opposite sides of the Earth. You've built a virtual instrument roughly 12,700 kilometers across. That's a bigger aperture than any physical structure humans have ever constructed or likely ever will construct. The Event Horizon Telescope is exactly that. It's not one telescope. It's a global collaboration linking radio observatories across multiple continents: Chile, Hawaii, Spain, Mexico, the South Pole, Arizona, synchronized using hydrogen maser atomic clocks, accurate to within a fraction of a second, recording data simultaneously onto hard drives that were then physically shipped to processing centers and correlated. The EHT effectively turned the entire planet into a single dish pointed at two targets. Getting those observatories to function as one instrument required that the atmospheric conditions at every site be acceptable on the same night, that the timing be exact, that the data correlation work cleanly across petabytes of raw observations. The logistics alone were staggering. In April 2019, the collaboration released the result of their first major campaign. The target was M87, the supermassive black hole at the center of the galaxy, Messier 87, sitting about 55 million light-years away with a mass of 6.5 billion suns. The image that appeared on screens around the world showed a bright asymmetric ring of glowing orange and yellow gas with a dark central region. That dark region, the shadow of the event horizon against the luminous surrounding plasma, was about 40 micro-arcseconds across. To give you a sense of what that means, it's equivalent to resolving a single human hair at a distance of roughly 500 kilometers. The image confirmed predictions from general relativity with striking precision. The ring's size, Its asymmetry caused by the rotation of the black hole dragging the surrounding gas faster on one side. The shape of the shadow, all of it matched what the equations said should be there. Event horizons had moved from mathematical objects to observable phenomena. You could look at that ring and understand that the dark center wasn't just a gap in the data. It was the actual boundary of no return, rendered visible by the gas falling into it. 3 years later, in 2022, the collaboration released the second image. This time the target was Sagittarius A SAC, the black hole at the center of our own galaxy. In some ways you'd expect this to be easier. It's far closer, only about 27,000 light-years away. But Sagittarius A is vastly less massive than M87. About 4 million solar masses compared to 6.5 billion. That means its event horizon is much smaller. It also means something more difficult. The gas swirling around Sagittarius AA orbits fast enough that it changes its brightness and structure on timescales of minutes. Imaging M87 time was like photographing a painting. Imaging Sagittarius AA was like photographing a fire. The data had to be processed using sophisticated statistical methods to reconstruct a stable average image from observations that were shifting the entire time they were being recorded. The result was another glowing ring surrounding a dark center. It looked almost exactly like what general relativity predicted. 2 black holes, wildly different in mass and distance, producing shadows that matched the same mathematical framework derived from Einstein's equations more than a century ago. What these images meant goes beyond confirming the math. We have now directly observed the boundary of no return around a black hole. Not inferred it, not calculated it, seen it. The event horizon is real in a way that only an image makes viscerally undeniable. That glowing ring changed the event horizon from a mathematical abstraction into something you can look at. It raised a question that pointed directly toward the rest of this story. If event horizons exist around individual black holes, what about the horizon that surrounds the entire observable universe? To understand the cosmic event horizon, you first need to understand what the observable universe actually is. And the answer is more unsettling than most people realize. When you look up at the night sky, you're not seeing the universe. You're seeing a bubble, a finite sphere of space centered on you, bounded by the farthest distance from which light has had time to reach us since the Big Bang. That boundary has a name. It's called the particle horizon, and it sits roughly 46.5 billion light-years away in every direction. That number probably stopped you. It should. The universe is 13.8 billion years old. Light travels at 186,000 miles per second. So if light has only been traveling for 13.8 billion years, how can we possibly see something 46.5 billion light-years away? That's more than 3 times farther than the light should have been able to travel. If you've never heard a satisfying explanation for this, you're not alone. It trips up a lot of people, and the answer gets at something fundamental about how the universe actually works. Space expands, not just the galaxies moving through space. The space itself stretches. While light was traveling toward us, the universe was growing, carrying those distant regions farther away. The light didn't travel 46.5 billion light-years. It traveled a much shorter distance through space that kept stretching beneath it, like walking forward on a moving walkway that's carrying you backward. The light still made it here, but the source that emitted it has since been carried far beyond where it started. To make this concrete, think about the oldest light we can detect. The cosmic microwave background, the faint glow of radiation left over from the early universe, was emitted when the universe was just 380,000 years old. That's ancient almost beyond comprehension, a time before any star existed. When that light was released, the region that emitted it was only about 42 million light-years away from where we are now. That's far, but it's manageable. In the time since that light left its source and traveled toward us, the universe expanded so dramatically that those same regions are now sitting roughly 46 billion light-years away. We can see them. Their ancient light is here, but they themselves are somewhere we could never reach, never visit, and never send a message to with any expectation of a reply arriving within the lifetime of the universe. Here's where the scale becomes genuinely hard to hold in your head. The particle horizon doesn't describe where things are right now. It describes where the sources of our oldest observable light were when they emitted it. The universe we see is a layered record of history, where the farthest objects we detect are also the earliest ones. Every telescope is a time machine. The farther you look, the further back in time you're seeing, and the edge of that, the particle horizon, is the moment of near total opacity just after the Big Bang. A wall of glowing plasma, some 46.5 billion light-years out. So what does this sphere actually contain? Current estimates suggest the observable universe holds roughly 2 trillion galaxies. Each of those galaxies contains billions to hundreds of billions of stars. The numbers become meaningless at a certain point, but the point is this: the observable universe is not small. It is not a compromise. It is an almost incomprehensible volume of space, and yet it represents a limitation, a hard boundary on what we can see right now given the age of the universe and the speed of light. But here's the thing that matters for where this is all going. The particle horizon is not fixed. It grows. Every year, light from regions slightly farther away has one more year to travel toward us, and the sphere of the observable universe expands accordingly. In principle, given enough time, the particle horizon inches outward. That might sound reassuring. It sounds like we'll eventually see more. In one narrow technical sense, that's true. But there's a second horizon, one that doesn't work that way at all. One that doesn't grow. One that's actually shrinking in the only sense that counts. This expansion has profound consequences that reshape our understanding of cosmic distance and possibility. As space stretches, distant galaxies recede from us at accelerating rates. Objects that were once within our theoretical reach are now permanently beyond it, separated not by distance alone, but by the expansion itself. Observations suggest the universe's expansion is accelerating, driven by a mysterious force physicists call dark energy. This acceleration fundamentally changes the calculus. The particle horizon, while technically growing over time, doesn't grow nearly as fast as space itself expands. In effect, the universe is pulling away from us faster than light itself can chase it down. The particle horizon tells you what you can currently see. It tells you the full history of light that has arrived, or will arrive, from every direction over the lifetime of the universe so far. That's a vast and meaningful boundary. But there is a separate question you could ask. Not what can we see right now, but what will we ever be able to learn from the universe in all of future time? What regions, however far away, could someday send us a signal that reaches us? Not yet, but eventually, if we wait. And what regions are already so far away and receding so fast that no signal they could send from this moment forward will ever close the gap? That second question has a different answer, a harder answer, and the boundary it describes is the cosmic event horizon, not the edge of what exists in our past, but the edge of everything that can ever reach us in our future. That distinction sounds subtle. It isn't. The particle horizon is the boundary of what we can currently see, but the cosmic event horizon is something different, something more absolute, and in some ways, far more disturbing. There's a distance in the universe beyond which everything is currently moving away from us faster than the speed of light. That boundary sits about 14.4 billion light-years away from Earth. It's called the Hubble sphere. And the moment you hear that galaxies beyond it are receding faster than light, the obvious question is, doesn't that break physics? Doesn't Einstein's special relativity say nothing can travel faster than light? The answer is yes. And also, this doesn't violate it at all. Understanding why requires a distinction that sounds technical but turns out to be critical. Special relativity prohibits matter or information from moving through space faster than light. That limit is absolute. But the expansion of the universe isn't objects moving through space. It's space itself stretching. The galaxies beyond the Hubble sphere aren't racing away from us like rockets. They're sitting still in their local neighborhoods, and the fabric of space between us and them is expanding at a rate that adds up to a recession velocity exceeding the speed of light. Relativity has nothing to say about how fast space itself can stretch. There's no law that caps it. The distinction sounds like a technicality until you follow it all the way through, and then it becomes one of the most important ideas in cosmology. Here's how the Hubble sphere is actually defined. The Hubble constant, written as h0, measures the current rate of expansion, roughly 70 kilometers per second for every megaparsec of distance. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance between us and a galaxy, that galaxy is currently receding at about 70 kilometers per second. Double the distance, double the recession velocity. The relationship is linear. That means there's a specific distance, 14.4 billion light-years, at which the recession velocity reaches exactly the speed of light. The further away a galaxy is, the faster it recedes. Now here's the part that genuinely confuses people. We can observe galaxies beyond the Hubble sphere. We have images of them. We've measured their redshifts. And that seems impossible if everything beyond the Hubble sphere is receding faster than light. How can light from those galaxies ever reach us? The answer is that the Hubble sphere isn't a fixed wall. It's defined by the current expansion rate, and the expansion rate has changed over the history of the universe. When a distant galaxy emitted the light we're detecting today, the universe was younger, denser, and expanding more slowly. The light started its journey in a region that wasn't yet receding faster than light. It entered our more local universe, continued traveling toward us, and eventually made it here. By the time that light arrives, the galaxy that sent it may be well outside the Hubble sphere, receding superluminally. But the photons themselves were already en route. They got out before the threshold shifted past their point of origin. Think about it this way. Imagine you're standing at the edge of a river, and the current is pulling water away from you. You throw a ball upstream. If the current is slow enough at the moment you throw it, the ball moves toward you even though it's in water that's flowing away. As the current picks up further downstream, it doesn't matter. The ball is already close enough to reach you. That's roughly the situation with light from beyond the Hubble sphere. It launched from a region that wasn't yet fully dominated by rapid expansion, and it managed to close enough distance to eventually arrive. What that means is that the Hubble sphere is emphatically not the boundary of the observable universe. This is one of the most common misconceptions in popular cosmology. The observable universe extends to roughly 46.5 billion light-years. The Hubble sphere sits at 14.4 billion. We're observing enormous volumes of space that currently lie beyond the Hubble sphere, because their ancient light is still streaming in. The observable universe's edge is defined by the particle horizon, the farthest point from which light has had time to reach us since the Big Bang. The Hubble sphere is something different. It's a description of what space is doing right now, not a limit on past signals. But here's where the Hubble sphere starts to matter in a deeper way. The expansion of the universe isn't constant, it's accelerating. That means the Hubble sphere has a dynamic relationship with the cosmic event horizon, the true boundary of future knowledge. Right now we can receive signals from regions beyond the Hubble sphere because those photons were already traveling when conditions were more favorable. But light emitted from certain distances at this moment, today, will never reach us. The accelerating expansion will stretch space fast enough to prevent it. That's a different boundary. That's the cosmic event horizon. The Hubble sphere describes where recession velocity equals the speed of light based on today's expansion rate. The cosmic event horizon describes something more severe, the farthest point from which any signal emitted now could ever arrive, not just in the next billion years, but in all of future time combined. In an accelerating universe, those two numbers are close but not identical. And the difference between them is not a small technical detail. It reflects something profound about the permanent structure of the universe and what information we will ever be able to access. Understanding why those two horizons, the Hubble sphere and the cosmic event horizon, are not the same thing is essential to understanding just how strange our universe really is. In 1998, two teams of astronomers independently announced something so unexpected that it took years for the broader scientific community to fully accept it. Both teams had been doing the same thing. They were studying Type 1a supernovae, exploding stars that burn with such consistent peak brightness that astronomers use them as standard candles, reference points for measuring cosmic distances. The idea was straightforward. Measure how fast the universe was expanding now. Compare that to how fast it was expanding in the past, and calculate how much gravity was slowing it down. That was the expectation. Gravity pulls matter together. Expansion should be decelerating. The only real question was how fast it was losing speed. What they found instead was that the expansion wasn't slowing down at all. It was speeding up. This wasn't just a minor correction to existing models. It fundamentally challenged the entire framework through which physicists understood the cosmos. Every cosmological calculation for decades had assumed a universe gradually decelerating under its own gravitational weight. This discovery suggested something radically different, a universe actively working against its own matter, pushing outward with an ever-increasing intensity. Saul Perlmutter led one team. Brian Schmidt and Adam Rees led the other. They reached the same conclusion independently, which is exactly the kind of confirmation that makes a result impossible to dismiss. The distant supernovae were fainter than they should have been, meaning they were farther away than any decelerating universe could explain. The universe wasn't breaking. It was accelerating. All three men were awarded the Nobel Prize in Physics in 2011 for this discovery. Here's where things get uncomfortable. For acceleration to happen, something has to be pushing outward. Something has to be overpowering gravity across the largest scales in the universe. The matter we can see, stars, gas, dust, galaxies, accounts for only a small fraction of what exists. Dark matter accounts for more. But even combining visible matter and dark matter, you still can't explain the acceleration. There has to be something else. Something that pushes rather than pulls. And whatever it is, it makes up roughly 68% of the total energy content of the universe. We call it dark energy. The name is somewhat honest. We call it dark because we can't detect it directly. We can only infer it from what it does. And what it does is drive space apart faster and faster, with no sign of slowing down. So what actually is it? The most widely accepted explanation is that dark energy is a property of empty space itself, not something that fills space, space itself. Every cubic meter of vacuum in the universe carries a small but non-zero energy. This is sometimes called the vacuum energy, or in the mathematical language of Einstein's equations, the cosmological constant. The symbol for it is the Greek letter lambda. That name has a history. Einstein introduced lambda in 1917, not because he thought the universe was accelerating, but because he thought the universe was static. Without some term to counteract gravity, his equations predicted the universe would collapse. So he inserted lambda as a kind of stabilizing constant, a way to make the math agree with what he believed the universe looked like. When Edwin Hubble confirmed that the universe was actually expanding in 1929, Einstein dropped lambda entirely. He reportedly called it his greatest blunder. It turned out he'd been more right than he knew. Lambda, the cosmological constant, is exactly the mathematical structure needed to describe dark energy. Einstein abandoned it for the wrong reasons, and the universe brought it back. The blunder wasn't inventing lambda. The blunder was throwing it away. Sometimes the most profound truths in physics come from equations that precede the experimental evidence confirming them by decades or even centuries. Einstein's genius lay not just in creating the mathematics, but in his willingness to follow where that mathematics led, even when it contradicted his intuitions about how nature should behave. Now here's what makes dark energy genuinely strange and genuinely terrifying in its implications. Because dark energy is a property of empty space, it doesn't dilute as the universe expands. Ordinary matter gets spread thinner as volume increases. Radiation weakens. But the energy of the vacuum stays constant per unit volume. As the universe grows, total dark energy grows with it. More space means more dark energy. More dark energy means faster expansion. Faster expansion means more space. You can see where this goes. This is not a gradual process that might eventually reverse. There's no point at which gravity catches up. Under current cosmological models, assuming dark energy remains constant, which is our best available assumption, the acceleration continues forever, increasing in effect indefinitely. Now ask yourself what this means for anything trying to travel across the cosmos. Light moves at 300,000 kilometers per second. That is the absolute speed limit of the universe. But if space between 2 points is expanding faster than light can cross it, then light emitted from one point will never reach the other. Not eventually. Not with more time. Never. The gap doesn't close. It widens. Before the 1998 discovery, this wasn't inevitable. A universe expanding but decelerating would eventually allow light from any distance to reach us, given enough time. The expansion would slow, the gaps would stop growing faster than light could bridge them, and in principle, signals from arbitrarily distant regions could eventually arrive. The universe would have no permanent edge to what it could communicate. Dark energy changes that entirely. With constant acceleration, a threshold distance exists beyond which light emitted today will never reach us. The expansion between here and there will always outpace the signal. That threshold is not a physical wall. There's no membrane, no surface, nothing to crash into. It's a boundary defined purely by the geometry of an accelerating space-time. But it's permanent in a way that no other boundary in science is permanent. It's not a limit we might one day work around. It's written into the equations of how the universe expands, and it exists because dark energy exists. Without dark energy, this boundary would be temporary or non-existent. Given enough time, light from anywhere in the universe could theoretically close the gap and reach us. But with acceleration, a permanent boundary forms, and that boundary is the cosmic event horizon. So where exactly is the cosmic event horizon? The answer is about 16 billion light-years away. That's the current best estimate, and it sounds enormous, because it is. But what that number actually means in practical terms is something most people haven't thought through. And once you do, it changes the way you look at everything beyond our galaxy. Here's what 16 billion light-years means. If a star explodes right now, at this exact moment in cosmic time, at a distance of 16 billion light-years, the light from that explosion will travel toward us forever and never arrive. Not because the star is too far away in any conventional sense, not because our telescopes aren't sensitive enough, but because the space between us and that star is expanding faster than the light can cross it. The light moves, the gap grows faster, the signal never closes the distance. That is the cosmic event horizon. It's not a wall. There's nothing physical sitting at 16 billion light-years marking the boundary. It's a threshold defined entirely by the relationship between light speed and the rate of cosmic expansion. Cross it, and causality cuts off. Nothing that happens on the other side of that line can ever affect us again. Now here's where this gets genuinely strange. The particle horizon, the edge of the observable universe, sits at roughly 46.5 billion light-years. That's the boundary of everything we can currently see. And you might notice that 46.5 billion is a lot larger than 16 billion. This is not a contradiction. These two numbers refer to two completely different things, and the gap between them is critical. The particle horizon tells you how far away the oldest light reaching us right now was emitted. The cosmic event horizon tells you how far away a source can be and still send you a signal that will eventually arrive. We can currently observe objects well beyond 16 billion light years because light those objects emitted billions of years ago is still traveling toward us, still in transit across space that was less expanded when the light first set out. That ancient light will keep arriving. We'll keep seeing those galaxies for billions of years to come. But here's the catch. We will never receive new information from those regions. Any signal they emit from this point forward is lost. The galaxy we're observing at 30 billion light years away, we're seeing it as it was in the deep past, because that's the only version of it that can ever reach us. The present-day version of that galaxy is already beyond the horizon. It has already crossed the threshold, and everything happening there right now is permanently unreachable. Think about what that actually means. There are galaxies we can see, real objects in our telescopes, that are already cut off from us in the most absolute sense possible. We're looking at their past. Their future is beyond the edge of what we can ever know. The specific value of the cosmic event horizon, that 16 billion light-year figure, comes directly from the Hubble constant and the density of dark energy. The Hubble constant, currently estimated at around 67 to 73 kilometers per second per megaparsec, depending on the measurement method, describes how fast the universe is expanding at any given scale. Dark energy, which makes up roughly 68% of the total energy density of the universe, determines how that expansion rate changes over time. Put those two things together, and you can calculate, using general relativity, the maximum come-moving distance from which a light signal emitted today could ever reach us. That calculation gives you 16 billion light years. If dark energy were weaker, the horizon would be farther out. If dark energy were stronger, it would be closer in. The horizon isn't a fixed feature of the cosmos. It's a consequence of the specific physics of this universe, this vacuum energy density, this expansion rate. In a universe without dark energy, there would be no permanent cosmic event horizon at all. Given infinite time, light from anywhere could theoretically cross any distance. It's the acceleration that creates the wall. This is what makes the cosmic event horizon categorically different from every other kind of limit in science. It's not that we need faster computers. It's not that we need bigger telescopes or more funding or another century of research. The information beyond 16 billion light years is not delayed or difficult to obtain. It is geometrically, permanently, physically inaccessible. The universe itself has encoded this boundary into the structure of space-time, and no discovery, no technology, no amount of time makes it negotiable. That's worth sitting with for a moment. Science has no shortage of things we don't yet know. But there's an enormous difference between things we don't know yet and things we can never know. The cosmic event horizon is the starkest example we have of the second category. It defines not the edge of our current knowledge, but the edge of all possible future knowledge, forever. And right now, right at this moment, you can see objects beyond that edge. Their ancient light is arriving. Their current state is already gone from us. That gap between what we can currently see and what we will ever be able to learn about is one of the most profound asymmetries built into the observable universe. There's a distinction in cosmology that trips up almost everyone the first time they encounter it, and it matters enormously for understanding what the cosmic event horizon actually means. When cosmologists talk about distances in an expanding universe, they're not all talking about the same thing. There are two separate ways to measure how far away something is, and they give you different numbers for the same object. Neither one is wrong. They're just answering different questions. But if you mix them up, the cosmic event horizon stops making sense entirely. The first type is called proper distance. This is the most intuitive version. It's the actual physical separation between 2 points at a specific moment in cosmic time. If you could somehow freeze the expansion of the universe and lay a ruler from here to a distant galaxy, the length of that ruler would be the proper distance. It's a real physical measurement. The problem is that it changes constantly. Every moment you wait, the universe expands, and the proper distance to that same galaxy gets larger. Proper distance is a snapshot. It tells you how far something is right now, but not the same galaxy tomorrow, and certainly not the same galaxy a billion years from now. The second type is comoving distance. This is where things get more abstract. Comoving coordinates are designed to move with the expansion of space, so that the coordinate position of a galaxy stays fixed, even as the universe stretches. Think of it like drawing dots on the surface of a balloon before you inflate it. As the balloon expands, the dots get farther apart in real terms, but their positions on the balloon's surface stay the same. Comoving distance is the measurement on the balloon's surface before inflation. It factors the expansion out entirely. Cosmologists prefer Combs moving distances because they make the math manageable. If you want to track galaxies across billions of years of cosmic evolution, you don't want your coordinate system constantly shifting underneath you. Combs moving coordinates give you a stable frame of reference. They let you map the large-scale structure of the universe in a way that doesn't change just because time is passing. Here's where this becomes critical for understanding the event horizon. When you hear that the cosmic event horizon sits at roughly 16 billion light-years, that's a Combs moving distance. In physical terms, right now, the proper distance to the horizon is also close to that value, but they're measuring the same boundary in two different frameworks. Over time, as the universe expands, the proper distance to the horizon grows. The actual physical distance to that boundary, measured in frozen ruler terms, increases steadily as space stretches outward. You might think that means the horizon is expanding, and in one sense it is. In proper distance terms, that boundary is moving outward, but that's the less important sense. In comoving terms, the coordinates that actually track which galaxies we're capable of receiving signals from, the event horizon is shrinking. The set of galaxies inside the comoving horizon is getting smaller over time. Today, any galaxy with a comoving position within about 16 billion light-years can still send us a signal that will eventually arrive. But as the expansion accelerates, that boundary contracts. Galaxies near the edge of the comoving horizon will cross it and join the permanently unreachable region. They won't have moved. Their comoving positions stay fixed by definition. What changes is the horizon itself, closing inward around us. This is the genuinely counterintuitive part. The universe is expanding. Everything is spreading out. You'd expect the region accessible to us to grow larger as well, But dark energy is accelerating that expansion, and the acceleration means future light signals face an increasingly steep battle to close the gap between themselves and us. The co-moving horizon doesn't expand to meet them, it retreats. A useful way to think about it: the proper distance to the horizon grows because space is stretching. But stretching space doesn't help light reach you faster. What matters is whether light emitted today from a given region can ever cover the co-moving ground between that region and us before the expansion renders it permanently impossible. As the acceleration continues, fewer and fewer regions meet that criterion. The qualifying list shrinks. So when someone says the cosmic event horizon is at 16 billion light-years and asks whether it's expanding or shrinking, the honest answer is both, depending on which distance you're using. And the one that matters for knowledge, for contact, for the universe's effective information budget, is the co-moving one. What that means practically is that as the universe ages, the co-moving volume of space from which we can ever receive information is steadily, irreversibly shrinking. Right now, beyond the cosmic event horizon, there are galaxies, not theoretical constructs, not mathematical placeholders, actual galaxies, hundreds of billions of them, containing stars that burn and age and die, orbiting planets that have formed from the same chemistry we see throughout the observable universe. They exist at this moment, right now, as you watch this, and the light they are emitting right now will never reach you, not because of distance alone, not because of any failure of technology, but because the geometry of space-time itself guarantees that every photon those galaxies release from this moment forward is already outpaced by the expansion of space between here and there. Think about what that actually means. Those galaxies aren't gone. They're not destroyed. There's no wall, no physical barrier, no event marking the moment they cross the threshold. They are simply on the other side of a boundary that physics drew across the cosmos, and nothing that happens on their side of that line can ever inform anything on ours. Here's where the cosmological principle becomes uncomfortable in a very specific way. One of the foundational assumptions of modern cosmology is that the universe looks roughly the same everywhere. No location is special, no direction is privileged. The structures we observe, galaxies, clusters, filaments, voids, should repeat statistically throughout the rest of the universe beyond what we can see. There's no compelling reason to think the regions beyond the cosmic event horizon are physically different from the ones you can observe on a clear night through even a modest telescope. The same laws of physics apply. The same hydrogen clouds collapsed under gravity, the same stellar furnaces ignited. If anything, the universe beyond the horizon is almost certainly populated in a way that mirrors and almost certainly dwarfs what we can observe. We simply can't observe it. That's the entire point. And that distinction matters enormously. This isn't ignorance we can cure with better instruments or longer observation times. It's a permanent feature of the universe we inhabit. But here's where it gets genuinely strange. Some of the objects you can observe right now with existing telescopes are already beyond the cosmic event horizon. They crossed that boundary some time ago. You're still seeing them because the light they emitted before they crossed is still traveling toward us. And that ancient light hasn't finished its journey yet. We're looking at those galaxies as they were billions of years in the past, before the horizon swallowed them, and will continue to receive that old light for a long time to come. But the galaxy as it exists today, that version is already gone from our future. We will never receive a photon from its present state. We are, in a very real sense, watching something that has already, permanently, receded beyond reach. We just haven't received the news yet. That's a genuinely disorienting situation. The image you see in the telescope is real. The galaxy is real, but the information in that image is a fossil. You're not seeing the galaxy. You're seeing a record of the galaxy from an era when it was still in our future, cosmologically speaking. The present-day version is silent. What happens as that ancient light finally runs out? It doesn't disappear all at once, it fades. As a galaxy recedes deeper and deeper beyond the horizon, the light it emitted progressively earlier in cosmic history continues to arrive, but stretched. The wavelengths get longer. The photons arrive less frequently. The galaxy dims and reddens in a process that, for a sufficiently distant source, plays out over billions of years. Eventually, the wavelengths stretch so far that no instrument we could ever build would detect them. The signal doesn't snap off. It just becomes quieter and slower and longer until the last detectable photon from that galaxy arrives, and then there is nothing after it. That last photon is the farewell. It carries information about that galaxy from some moment in its distant past, and it's the final information that galaxy will ever send us. After that, from our perspective, the galaxy simply ceases to exist as an observable entity. The universe doesn't announce this. There's no marker in the sky. One moment there is an astronomically faint signal, and then there isn't one anymore, and no amount of waiting will produce another. And it isn't one galaxy. It isn't 1,000. There are entire clusters, entire superclusters, entire cosmic filaments on the far side of the event horizon. The structures beyond it are almost certainly comparable in scale and richness to the cosmic web we've spent decades mapping. The great surveys of the observable universe, hundreds of millions of galaxies charted across billions of light years, represent a fraction of what exists. Just not a fraction we will ever access. What's worth sitting with is the asymmetry here. We have a window into the past that extends remarkably far. Ancient light is still reaching us from regions already beyond our future reach. We are receiving information right now from a universe that is, in practical terms, already larger than the one we can ever interact with. That window is closing, slowly, on any human timescale, but closing. The moving volume from which new signals can ever arrive is not static. It contracts. Every moment that passes, the set of locations that can send us a message in any possible future gets a little smaller. We are watching the last ancient signals from those regions travel toward us across billions of years, knowing that when they finally arrive, those galaxies will be permanently, irretrievably beyond the edge of what our universe can ever contain. Every single second, roughly 20,000 stars slip permanently beyond our cosmic event horizon. Not because they explode or collapse, not because anything catastrophic happens to them. They simply drift past a threshold. From that moment forward, every photon they emit travels toward us through a space that is expanding faster than the light itself can cross. Those stars still exist. They're still burning. We will never know it again. Think about what that rate actually means. 20,000 stars per second. In the time it takes you to read this paragraph, hundreds of thousands of stars have crossed that boundary. In a single year, that adds up to something in the neighborhood of 630 billion stars vanishing from the set of things we can ever learn about. The universe isn't waiting for us to catch up. It's actively, continuously pulling itself out of our reach. It's doing so at a rate that makes the loss essentially incomprehensible at human scales. Right now, the observable universe contains roughly 2 trillion galaxies. That number is already staggering on its own, but here's what makes it genuinely unsettling. That 2 trillion figure is a snapshot of a universe that is already disappearing. Many of those galaxies are already beyond the cosmic event horizon in the sense that new light they emit today will never reach us. We're still seeing their ancient signals, light that left millions or billions of years ago, before those galaxies crossed the threshold. When that old light finally arrives, and there is nothing following behind it, those galaxies will go permanently dark, not because they died, but because the universe stretched the gap past the point of no return. In a few billion years, the situation gets dramatically more extreme. Every galaxy beyond our local group, the few dozen galaxies gravitationally bound to the Milky Way, will have receded so far that not even their ancient light remains in transit toward us. The Virgo cluster, which contains over 1,000 galaxies and sits about 65 million light-years away, will be gone. The Coma cluster, the Perseus cluster, the great filaments and walls that define the large-scale structure of the cosmos we know, all of it will have receded past the horizon. Nothing behind but an expanding ocean of empty space, punctuated by the merged remnant of our own galaxy and a handful of close companions. An astronomer living at that time, let's say 150 billion years from now, would look out at the sky and see essentially nothing. No external galaxies, no evidence of large-scale cosmic structure. And here's the part that should genuinely disturb you. That astronomer would have no way of knowing what had been lost. They'd build their models of the universe based on what was observable to them. Their observations would be consistent, coherent, and almost entirely wrong about the broader picture. They'd have no Hubble flow to measure, no cosmic microwave background to detect. It would have stretched to wavelengths far beyond any practical instrument, and no distant supernovae to reveal that the universe was ever accelerating at all. They might reasonably conclude that the universe is static, eternal, and isolated. Every tool we use to reconstruct cosmic history would simply no longer exist in any form they could detect. Their cosmology would be internally consistent. It would just be profoundly incomplete. Now sit with that for a moment and ask a harder question. How do we know that hasn't already happened to us? The universe is 13.8 billion years old. Dark energy has been accelerating the expansion for roughly the last 6 billion years. Whatever was pushed beyond the horizon before we existed, before life existed, before the Earth formed, that information is already gone. Not archived somewhere we can't access, just gone. The cosmic event horizon has been operating the whole time. There could have been large-scale structures, patterns, or distributions of matter in the early universe that would have told us something fundamental about the conditions of the Big Bang or the nature of inflation. If those structures happen to exist in regions that receded beyond our horizon before we could observe them, we'd have no way of knowing they existed, no way of knowing that we're missing something. The universe has a built-in memory problem, and it's not subtle. It's a hard physical constraint that operates on the same level as the speed of light. This isn't a problem technology can fix. You can't build a more sensitive telescope to detect light that never arrived. You can't extrapolate your way to information that was geometrically severed from your location before it could reach you. What's gone is gone, in a more absolute sense than almost anything else in science. Most gaps in human knowledge are gaps in principle closable. This one isn't. The data was destroyed not by human failing or technological limitation, but by the structure of space-time itself. What we have right now in this specific era of cosmic history is a window, not a permanent feature of the universe. A window. The cosmic microwave background is detectable. External galaxies are visible. The large-scale structure that tells the story of how the universe grew from tiny quantum fluctuations into everything we see is laid out in front of us in enough detail to reconstruct what happened. That window is closing, not quickly by human standards, but it is closing, and nothing will reopen it. We are, in a very real sense, fortunate to exist now, at a moment when enough of the universe is still visible to reconstruct what happened. This was because the evidence is already being erased, and eventually, it will simply be gone. About 100 billion years from now, an astronomer living in what remains of the Milky Way will look out at a night sky that appears fundamentally different from ours. Every galaxy beyond the local group, every single one of the roughly 2 trillion galaxies we can currently observe, will have crossed the cosmic event horizon, not destroyed, not extinguished, simply gone, receded beyond the boundary from which no light can ever return. The sky that astronomers sees will be dark in a way ours never has been, and they will have no particular reason to suspect anything is missing. What they'll actually be living inside is the merged remnant of the Milky Way and the Andromeda Galaxy, a collision that begins in about 4 billion years and plays out over billions more. Astronomers already have a name for the result: Milkdromeda. It won't be a dramatic wreck of tangled stars. Most stars in both galaxies are so far apart that the merger will pass largely without direct collisions. 2 vast clouds of stars interpenetrating and settling into a new configuration. The result will be a single large elliptical galaxy, gravitationally bound, permanent, and surrounded by a handful of smaller local group members. That's all. The rest of the cosmos will be completely inaccessible. Think about what that means for the cosmic microwave background. Right now, that ancient radiation, the afterglow of the Big Bang, emitted 380,000 years after the universe formed, fills the sky in every direction at a temperature of about 2.7 Kelvin. It's already cold. It's already been stretched by cosmic expansion for 13.8 billion years. In 100 billion years, that radiation will have been stretched by another factor of roughly 7. The wavelengths will be so long, so extraordinarily low in energy, that no physically conceivable detector could measure them. The cosmic microwave background won't disappear with a bang. It will simply fade below any possible threshold of detection, and it will be gone. Here's where things get genuinely uncomfortable. Those future astronomers won't just be missing data. They'll be missing the single most important piece of observational evidence for how the universe began. The CMB is the cornerstone of modern cosmology. It confirmed the Big Bang. It revealed the density fluctuations that seeded every galaxy and cluster we observe. Without it, there is no direct thermal evidence for an early hot dense universe. Future observers won't have a gap in their data where the CMB used to be. They'll have no reason to go looking. To them, the background radiation simply won't exist. The Hubble flow will be gone too. Right now, one of the most powerful tools cosmologists have is the observation that distant galaxies are receding at velocities proportional to their distance. Measure the recession velocities of enough galaxies in enough directions, and you can map the expansion of the universe directly. You can determine that expansion is accelerating. You can calculate dark energy's contribution to the total energy density. In 100 billion years, those external galaxies won't be there. An astronomer in Milkdromeda will look out and see a static island of stars surrounded by void. The universe won't appear to be expanding. It won't appear to be doing anything at all. It will look eternal and unchanging, because there will be nothing left to measure the change against. Those future scientists won't be ignorant. They'll be sophisticated. They'll have particle physics and local stellar dynamics and every tool available to observers within a gravitationally bound system. They'll construct cosmological models and test them rigorously against everything they can observe. And they'll arrive at a picture of the cosmos that is wrong, not because of any failure of intelligence or method, but because the evidence that would have corrected them no longer exists. Their models will be internally consistent. Every observation they can make will fit. The universe will simply have lied to them through omission, and they'll have no way to know it. That is the philosophical weight here. The universe is not a neutral archive. It does not preserve its own history. The accelerating expansion driven by dark energy is actively erasing cosmological information on a timescale that is long by human standards, but finite and inevitable by any absolute measure. Every second that passes, the observable record of the universe's origin grows slightly thinner. In 100 billion years, the erasure will be so complete that no civilization starting fresh could ever reconstruct what we already know today, which raises the question you probably don't want to sit with for too long. What evidence did we miss? The universe is 13.8 billion years old. The cosmic event horizon has been contracting in comoving terms since dark energy began to dominate, roughly 5 billion years ago. Structures and events that existed in regions that have already crossed beyond the horizon are permanently gone from our observable record. We don't know what was there. We can't know. We assume, because the cosmological principle gives us reason to, that those regions were similar to what we observe. But assumption and evidence are different things, and some distinction between the two may have already been erased before any telescope was ever built. Our cosmological picture may be complete. The evidence suggests a remarkably coherent model, but there is no way to verify whether the universe has already quietly removed something we needed, something that would have forced a different conclusion. The same mechanism that will blind those future astronomers to the Big Bang has been running since long before humans existed. We are downstream of a process of erasure that we didn't choose and cannot stop. It will be a universe that has forgotten what it once was, and there will be nothing any civilization, however advanced, could do to recover that lost history. In 1974, Stephen Hawking published a paper that, if taken at face value, appeared to break one of the most fundamental laws of physics. The law in question was the conservation of information. In classical physics, information is never truly destroyed. Every event leaves a record. Every cause has a traceable effect. Burn a book and you've scattered atoms, but in principle, if you could track every particle, you could reconstruct what was written. That principle sits at the foundation of both classical mechanics and quantum mechanics. Hawking's paper suggested that black holes might violate it completely. Here's what he found. Quantum mechanics tells us that empty space isn't actually empty. At the smallest scales, particle and antiparticle pairs flicker into existence continuously, appearing out of the vacuum, annihilating each other almost instantly, and vanishing again. Under normal circumstances, this is a closed loop. The pairs appear and disappear without leaving any lasting effect. But near the event horizon of a black hole, something different can happen. One particle from the pair can fall across the horizon while the other escapes. The escaping particle carries energy away from the black hole. The infalling particle carries negative energy inward. The net result is that the black hole loses mass, slowly and continuously, radiating energy outward as a faint thermal glow. That glow is what Hawking predicted. It's now called Hawking radiation. The temperature of this radiation is extraordinarily small for any black hole we know of. A stellar mass black hole radiates at a temperature of roughly 60 billionths of a Kelvin. Supermassive black holes are even colder. For all practical purposes, Hawking radiation is undetectable with any instrument we currently have. The cosmic microwave background, the ambient thermal radiation left over from the Big Bang, is about 2.7 Kelvin, billions of times hotter than the Hawking radiation from any known black hole. The radiation is drowned out completely, but the prediction isn't about what we can measure right now. It's about what the laws of physics require. And those laws, if Hawking was right, require that black holes eventually evaporate. Given enough time, and we're talking timescales that make the current age of the universe look like a rounding error, a black hole will radiate away all of its mass and disappear entirely. Stellar mass black holes would take something like 10 to the power of 67 years to evaporate. Supermassive black holes would take far longer, but the endpoint is the same. The black hole is gone. Here's where things get uncomfortable. When the black hole formed, it swallowed matter. Stars, gas, planets, perhaps entire civilizations. All of that material carried information, precise quantum states, structure, history. If the black hole evaporates completely, and Hawking radiation is purely thermal and carries no information about what fell in, then all of that information is simply gone, destroyed, not scattered or diluted, but permanently erased from the universe. And that would violate one of the deepest principles in physics. This is the black hole information paradox, and physicists have been arguing about it for 50 years. Some argue the information is somehow encoded in the Hawking radiation in a way that's too subtle to calculate with current tools. Others argue the black hole doesn't evaporate completely, but leaves behind a stable remnant that preserves the information. Others still argue that the paradox reveals a fundamental incompatibility between general relativity and quantum mechanics that won't be resolved until we have a full theory of quantum gravity. Nobody has solved it yet, not definitively. Now here's the part that connects back to everything we've been discussing about the cosmic event horizon. In 1977, Gary Gibbons and Stephen Hawking extended the same reasoning and found that the cosmic event horizon has a temperature too. The accelerating expansion of space creates a horizon in the same mathematical sense that a black hole's gravity creates one. And just as quantum effects near a black hole's horizon produce radiation, quantum effects near the cosmic event horizon produce a thermal bath of particles. The temperature associated with our cosmic event horizon, called the Gibbons-Hawking temperature, is approximately 10 to the power of negative 30 Kelvin. That's not just cold. That's cold in a way that's almost impossible to express meaningfully. The coldest temperatures ever achieved in a laboratory are millions of times hotter than this. The number is real, but it exists so far below anything physically accessible that it functions more as a theoretical statement than a measurement. What it says, though, is profound. The cosmic event horizon is not just a geometric boundary. It has thermodynamic properties. It has an entropy. It radiates. The same deep structures that connect black hole horizons to quantum mechanics and thermodynamics also connect the edge of the observable universe to those same principles. That is not a coincidence. It suggests that horizon physics is pointing at something fundamental about the relationship between gravity, quantum mechanics, space-time, and information that we don't fully understand yet. The information paradox for black holes is hard enough. The equivalent question for the cosmic event horizon, what happens to information as galaxies slip permanently beyond it, as their quantum states become causally disconnected from ours forever, is even less resolved. The universe's own horizon has a temperature, impossibly small but theoretically real, and what that ultimately means for the fate of information in our cosmos remains one of the most fiercely contested questions in all of theoretical physics. Here's a problem that kept cosmologists awake for decades. When we map the cosmic microwave background, the faint afterglow of radiation left over from the early universe, we find something that shouldn't be there. The temperature of that radiation is almost perfectly uniform across the entire sky. Not roughly uniform, not approximately uniform. Uniform to within 1 part in 100,000. That sounds like a good thing at first. It suggests the early universe was extraordinarily smooth and even. But when you think carefully about what that uniformity requires, it stops being reassuring and starts being deeply troubling. Here's why. The observable universe spans roughly 93 billion light-years from one edge to the opposite edge. Two regions sitting on opposite sides of that expanse have never been in causal contact. Light from one side has never reached the other side. In 13.8 billion years, there simply hasn't been enough time for any signal to travel between them. And yet their temperatures match. Not because they exchanged energy and equilibrated the way a hot cup of coffee gradually reaches room temperature. They couldn't have. They've never interacted at all. They shouldn't know anything about each other. This is the horizon problem, and for a long time no one had a satisfying answer to it. Think about what it would take to produce that result without some explanation. Imagine two rooms that have never been connected by any door, any pipe, or any wire. You open both rooms and measure the temperature inside each one. They're identical to within a fraction of a degree. You'd immediately suspect something connected them before you looked. That's exactly the situation cosmologists found themselves in. The uniformity of the CMB was screaming that something connected those distant regions, but the standard Big Bang model without any additions had no mechanism that could do it. The solution came in 1980 when physicist Alan Guth proposed cosmic inflation. The idea is striking in its simplicity, even if the physics underneath it is anything but. In the first unimaginably brief window of time after the Big Bang, somewhere between 10 to the negative 36 and 10 to the negative 32 seconds, the universe underwent an exponential expansion so extreme that it dwarfs anything we've discussed in this series so far. In far less time than it takes light to cross a single proton, a region smaller than an atom was stretched to a size larger than the observable universe is today. Space didn't just expand, it exploded outward at a rate that makes the current cosmic expansion look essentially motionless by comparison. Before inflation, that tiny region was causally connected. Every part of it had been in contact with every other part. Temperatures had equalized, conditions had smoothed out. Then inflation stretched that connected region so violently that what had been a microscopic uniform patch became the vast expanse we now call the observable universe. The regions we see on opposite sides of the CMB sky weren't always separated by 93 billion light-years. They were once neighbors, close enough to exchange energy and reach thermal equilibrium. Inflation pulled them apart so fast that they never had a chance to diverge. This is where event horizon physics enters the picture in a way most people don't expect. Inflation didn't just stretch space, it created event horizons. During the inflationary period, the expansion was so rapid that regions which had been in causal contact were suddenly pushed beyond each other's reach. A temporary event horizon formed, separating the pre-inflationary universe into patches that could no longer communicate. Those horizons weren't permanent. Inflation eventually ended, and the universe transitioned into the slower expansion we observe today. But the boundaries they created left imprints. The quantum fluctuations that existed in that tiny pre-inflationary region were frozen in place as inflation stretched them to cosmic scales. Those frozen fluctuations became the seeds of everything: galaxies, clusters, the large-scale structure of the universe. The 1 in 100,000 temperature variations in the CMB are those fluctuations stretched across the sky. What this means is that event horizons aren't only relevant to the future, they were shaping the universe before a single atom had formed. The same concept we've been applying to black holes and to the accelerating expansion of space today was operating in the first fraction of a second of cosmic history. The universe has been defined by event horizons since its very first moment. Inflation also carries a sobering implication. If the exponential expansion stretched our visible universe from a subatomic patch, then the full extent of what exists beyond our particle horizon, the universe beyond anything we can ever see, is almost certainly vast beyond meaningful comprehension. Some models suggest it's infinite. Others suggest regions with different physical constants, different structures, different laws. We can't know. Inflation predicts that what we call the observable universe is a tiny, smooth sample of something far larger, and the event horizons created during inflation are part of the reason we'll never access the rest of it. The same physics governing the event horizons we've been discussing was present at the very first moments of the universe, shaping everything we have ever been able to observe. Let's try to hold all of these boundaries in mind at once, because the comparison between them is one of the most striking things in all of cosmology. We've covered a lot of ground tonight: black hole event horizons, the Hubble sphere, the cosmic event horizon, the particle horizon. Each one represents a point of no return, a boundary enforced not by walls or barriers but by physics itself. But when you line them all up together, the progression is almost incomprehensible, and that's exactly why it's worth doing. Start at the bottom. Earth's Schwarzschild radius is about 9 millimeters. That's roughly the size of a marble. Compress every ocean, every mountain range, every continent, the entire mass of this planet into a sphere smaller than the one sitting at the bottom of a child's toy box, and you get a black hole. That's all it takes. The Sun's Schwarzschild radius is about 2.95 kilometers. Not the Sun's actual radius, which is 696,000 kilometers, but the size it would need to be compressed to. Less than 3 kilometers across. The entire Sun. A boundary you could walk across in under an hour if the physics of doing so weren't immediately fatal. Now move up. Sagittarius AC, the supermassive black hole at the center of our galaxy, has an event horizon spanning roughly 12 million kilometers. That's about 17 times the diameter of the Sun. Its boundary extends further than the distance between the Sun and Mercury. You could fit the entire inner solar system inside that event horizon and still have room. That's not a point. That's a region of space. And Sagittarius AC is not even close to the largest we know of. M87, the black hole the Event Horizon Telescope imaged in 2019, has an event horizon larger than the orbit of Neptune. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. M87's boundary swallows that entire span. Our entire solar system, all 8 planets, the Kuiper Belt, billions of kilometers in every direction, would fit inside it. Then there's TON 618, one of the most massive black holes ever measured, at roughly 66 billion solar masses. Its event horizon stretches across a distance that would take light weeks to cross. Hundreds of solar system widths. It's not a point in space. It's a region the size of a small corner of a galaxy. And yet none of these come close to the scales we're dealing with when we talk about the universe itself. The Hubble sphere. The distance at which galaxies are currently receding at exactly the speed of light sits at about 14.4 billion light-years. 1 light-year is roughly 9.5 trillion kilometers. The Hubble sphere is 14.4 billion of those. The cosmic event horizon extends a little further, to about 16 billion light-years. And the particle horizon, the full radius of the observable universe, reaches out to 46.5 billion light-years in every direction. Here's a comparison that might help those numbers land. If you scaled the cosmic event horizon down to the size of Earth's orbit around the Sun, roughly 300 million kilometers across, the observable universe at that same scale would be about the size of a basketball court. That's the proportional difference between the cosmic event horizon and the particle horizon. We can currently see far beyond our event horizon because ancient light is still arriving, but the region from which we'll ever receive new information, from this moment forward, is that much smaller. A basketball court versus Earth's orbit. That's the gap between what we can see and what we can ever learn. What makes this paradox so strange is that the cosmic event horizon is smaller than the observable universe, and yet it's the cosmic event horizon that defines all future knowledge. Everything we currently see beyond 16 billion light-years is operating on borrowed time. We're receiving old signals. Those galaxies are already gone from our future. The particle horizon tells us where the light has come from. The cosmic event horizon tells us where information can still come from. Those are not the same question, and the difference between them is the difference between the universe's past and its future. Beyond the particle horizon, the universe continues. How far? We don't know. Current models suggest it could be vastly larger than the observable portion, possibly infinite. The part we can see is just a bubble, and the part we'll ever learn anything new about is a smaller bubble still. Each horizon we've covered tonight is a layer of that reality, a nested set of boundaries that gets more absolute the further out you go. And sitting at the center of all of it is us, on a pale blue dot orbiting an ordinary star, in a universe that stretches further than we can see, and further still beyond the edge of what we can ever know. Most of the universe is already beyond our reach, and there is nothing we will ever do about that. Not eventually. Not with better telescopes or faster computers or some future breakthrough we haven't imagined yet. The information beyond the cosmic event horizon isn't hidden. It's gone, structurally and permanently, by the rules of the universe itself. This isn't a technological problem. It's not a funding problem. It's a feature of the geometry of space-time, and it applies equally to every civilization that has ever existed or will ever exist inside this observable bubble we call home. That's worth sitting with for a moment. When we talk about the limits of science, we usually mean the limits of current science. There's always the implication that with enough time and ingenuity, the gap closes. Here, the gap doesn't close. You could wait 1 trillion years. You could build instruments that fill entire solar systems. You could solve every equation in physics and the answer would be the same. What lies beyond the cosmic event horizon will never send you a signal. The physics won't allow it. And here's what makes that genuinely strange. We're not talking about empty space out there. We're talking about galaxies, real ones. Stars, planets, the full inventory of cosmic structure. Based on the cosmological principle, the foundational assumption that no location in the universe is physically special, those regions should look essentially like ours. The same distribution of matter, the same large-scale structure, the same basic physics. We have no reason to believe otherwise, and we have absolutely no way to verify it. That assumption is sound. It's the best we can do, but it will never be more than an assumption because the evidence that would confirm or contradict it cannot reach us. Think about what that means for something like the search for extraterrestrial intelligence. The observable universe alone contains an estimated 2 trillion galaxies. Beyond the cosmic event horizon, that number continues, possibly without limit. Civilizations could exist out there. Civilizations far older than ours, with histories and knowledge that dwarf anything we've accumulated. They could be trying to communicate. Their signals could be aimed directly at us, and none of it would matter, because the expansion of space ensures those signals will never arrive. Not ever. We wouldn't even know what we were missing. What's striking about this is how quiet it all is. Galaxies don't vanish in explosions. There's no visible boundary you could point a telescope at. Space simply expands, slowly and constantly, and the light that was traveling toward you falls a little further behind with each passing second, until one day it stops gaining ground entirely. No drama, no cataclysm, just absence. The universe removes things from knowability the way fog erases a shoreline, gradually, silently, and without apology. That indifference is genuinely difficult to internalize. We're used to thinking of knowledge as something that accumulates. Every generation learns more than the last. Every new instrument opens a wider window. But the cosmic event horizon represents a direction in which that curve bends back. The window isn't opening on that side. It's closing. Has been closing since dark energy began accelerating the expansion billions of years ago. We happen to exist at a moment when the window is still large enough to reveal the structure of the universe, to detect the cosmic microwave background, to map the distribution of 2 trillion galaxies. Future observers won't have that. We're the fortunate ones, and most of us have no idea. So does knowing about the horizon make the observable universe feel smaller? Smaller, no. But it does change the texture of it. Every galaxy you can see is one that still has time, finite time, to send you information. Every photon arriving from a distant cluster is a message that made it through before the door closed. The universe you can observe isn't just big, it's the complete set of everything that will ever be knowable to anyone living here. That's a different kind of weight. There's something almost personal about it when you take it seriously. The cosmic event horizon isn't out there somewhere, abstract and irrelevant. It defines the boundary of everything that can ever matter to us physically, observationally, empirically. Beyond it, reality continues. We just can't reach it, and it can't reach us, and neither side will ever know the difference. You can find that bleak if you want to, or you can turn it around. The observable universe contains more stars than there are grains of sand on every beach on Earth. It contains structures so large they take hundreds of millions of light years to cross. It contains phenomena we haven't explained, forces we don't fully understand, and a history stretching back 13.8 billion years. All of that is on this side of the line. All of that is still yours to ask questions about. The cosmic event horizon doesn't diminish the universe. It reminds us that even within the boundaries of what we can see, there is more than we will ever exhaust. Tonight, we've traveled from the surface of a collapsing star to the edge of everything that can ever be known. That's not a small journey. We started with a marble, 9 millimeters, the entire mass of this planet compressed to something you could lose in a couch cushion. From there, we scaled outward through event horizons measured in kilometers, then millions of kilometers, then distances larger than solar systems, and then we crossed into something different entirely. Not the horizon around a single collapsed object, but the horizon around everything we will ever be able to observe. The edge, not of a black hole, but of knowledge itself. Think about what that actually means. There is no more powerful telescope that closes this gap. There is no propulsion system, no future civilization, no amount of patience or ingenuity that gets you past that boundary. The cosmic event horizon isn't a problem waiting to be solved. It's a feature of the universe. It's written into the geometry of space-time the same way the speed of light is written into Maxwell's equations. It simply is. And here's what I find genuinely striking about all of this. Every other limit we've ever encountered in science has eventually yielded to something. Better instruments, smarter methods, more time. This one doesn't. The galaxies beyond that horizon are gone from us permanently, not because of distance alone, but because space between us and them is growing faster than light can cross it. They exist right now. They're probably full of stars, planets, whatever the universe puts in places like that. And none of it will ever reach us. Not one photon. Not one signal. When you go outside tonight and look up, some of the light landing on your eyes is ancient. We're talking billions of years of travel. And some of it, from galaxies already beyond our cosmic event horizon, is among the last signals those regions will ever send us. The universe is still delivering old mail, but the sender is already gone. If you've made it this far and you find yourself looking at the sky a little differently now, that's the whole point. That curiosity, that instinct to look up and ask what's out there and whether we can ever really know, that's not a small thing. If you want to keep exploring questions like this one, consider subscribing. It costs nothing, and it means more of this reaches people who are curious about how the universe actually works. We cover things that are genuinely hard to wrap your mind around, and we try to be honest about the parts that remain unsolved. The observable universe is enormous. Hundreds of billions of galaxies, each one a collection of hundreds of billions of stars, all of it visible in principle to any instrument patient enough to look, and beyond that, separated from us by the most absolute boundary physics can produce, something more, something we will never see. Sleep well tonight, knowing that the universe stretches on beyond what you can see, beyond what you will ever see, and that somehow, improbably, you are here to know it.